Okay, hello, and welcome to, I guess this is lecture 3, isn't it? Where we left off at the end of the last lecture was we were working on this sheet here. This is the one that says scientific notation and metric prefixes, because we just went over the metric prefixes, and so we want to get some experience with that, and also scientific notation. So as you'll notice in the first section of the sheet, it says, express the following measurements using scientific notation. So this is not practice with a metric system yet, so much as scientific notation. And it begins with the number 0.0056 seconds, and we have to put that in scientific notation. And that's number 1. Number 2, and I'm going to write down all of what they give us, and then you can pause the video and try to do the, try to get the answers yourself, and then we can compare notes once you start the video up again. Okay, the second one is 480,000. Oops, 480, oh, one more zero. Meters. 3 is 7,750 meters. 4 is 0.0806 square centimeters, and 5 is 0.0000960 cubic meters. Let me count 1, 2, 3, 4. Okay, just had to count and make sure I had the right number of zeros at the beginning there. See, this is one of the reasons you want to use scientific notation for really big or really small numbers, because I had to go back and count the zeros and make sure I had the right number. You wouldn't have to do that if you're using scientific notation. And so now why don't you pause the video and try and see what you come up with for the solutions to these, and then we'll come back. Okay, so now if we're back, we'd look at each of these numbers, and we would try to convert them to scientific notation, of course. Remember, for scientific notation, you need the first part of the number to be between 1 and 10. And so you can find where the decimal point is. In this first number, it's right here. And move it until you get a number that's between 1 and 10. In order to make this number between 1 and 10, we obviously have to move the decimal point to the right. And we move it 1, 2, 3 spaces. If you stop at 2 spaces, you've got 0.56, and that's not between 1 and 10. 5.6 is between 1 and 10. So 5.6 times 10 raised to a power. That power is going to be 3 because we moved the decimal point 3 times. And because when we moved the decimal point, we made the number bigger, the 3 has to be a -3 to compensate for making the first part of the number bigger. And also just remember that numbers less than 1 have negative exponents, numbers greater than 1 have positive exponents. So it is indeed -3. 5.6 times 10 to the -3. For this next one here, 480,000, again, you have to find the decimal point. That right there is a comma, not a decimal point. I tend not to put commas in numbers like this because it's easy to confuse a comma and a decimal point, especially if you're typing something. If it's a small font, especially, or in certain fonts, decimal points and commas tend to look alike. What I usually do when I'm typing a number like this is I'll leave a space. So I'll often go 480 space 000. That's actually the way they tend to do it in Europe, rather than using commas. In fact, in Europe, they use commas as decimal point, which is really confusing. But yeah, they tend to leave a space instead of a comma. So that's what I tend to do when I'm typing. When I'm writing, I'll often put a comma in, but I'll really exaggerate it to make it clear that it is a comma. So that is a comma. That's not a decimal point. There is no decimal point in this number. And as I said yesterday, when there's no decimal point in a number, you can assume that the decimal point is at the end of the number. But in this case, because we got a bunch of zeros at the end of the number, having a decimal point there versus not having it would affect the number of significant figures. So I'm going to write the decimal point in, but I'm going to put it in parentheses just to remind me that it wasn't there originally. Okay, so to get this number to be between 1 and 10, you have to move the decimal point to the left this time. 1, 2, 3, 4, 5 spaces. So we end up with 4.8. And remember, there was no decimal point there originally, so all those zeros at the end don't count as significant. So in scientific notation, the first part of the number would just be 4.8 times 10 raised to the power of the number of spaces you move the decimal. 1, 2, 3, 4, 5. And because moving the decimal point made the first part of the number smaller, 4.8 is much smaller than 480,000, that means that the exponent is positive to compensate for making the first part of the number smaller. And also remember that big numbers have positive exponents and small numbers have negative exponents. Okay, so next we have 7,750. Again, no decimal point, so you can assume that the decimal point is implied, but it's at the end. And again, I'm going to put it in parentheses so that I'll remember that it wasn't there originally. And we move the decimal point to the left again, 1, 2, 3 spaces, and then we get 7.75. But remember, the 0 at the end was not significant because there was no decimal point there to begin with. So you don't include that 0 in the scientific notation. You only include zeros in scientific notation if they are significant. Okay, then we need the power of 10. This is a big number, so it's going to be positive. Also, moving the decimal point makes the number smaller, so that also tells you that the exponent's going to be positive. And we moved the decimal 3 spaces, so the power is going to be positive 3. 7.75 times 10 to the third. Coming to the next one, 0.0806. The numbers at the beginning are not significant because zeros at the beginning of a number are never significant. That 0 there between the 8 and the 6 is significant, though, because it comes between numbers that are not zeros. So zeros in the middle of a number, as it were, are always significant. When we move the decimal point to get the number to be between 1 and 10, we have to move it 1, 2 places to the right. So 8.06 times 10 raised to some power. Now the original number was less than 1, so we would expect the power to be negative. Also, moving the decimal point made the number bigger, so we have to compensate with a negative exponent. And we move the decimal point 2 spaces, so the exponent is going to be 2. 8.06 times 10 to the minus 2. All right. Okay, here's the fun one. 0.0000960. Zeros at the beginning of a number, like I said, are never significant, so you don't have to worry about those. Zeros at the end of a number are significant if there is a decimal point anywhere in the number. There's your decimal point way back there at the beginning. So that counts. That means that this 0 counts as significant. So you got a 3-digit number, and you have to move the decimal point 1, 2, 3, 4, 5 spaces, which gives us 9.60. Again, include that last 0 because it is significant. And that's going to be times 10 raised to a negative power because this number is less than 1. And the original number, that is, was less than 1. And we move the decimal 1, 2, 3, 4, 5 spaces. So that'll be 9.60 times 10 to the minus 5. And that would be your proper scientific notation for that number. Okay, next we come to Roman numeral 2. Getting fancy here with the Roman numerals. Okay. Here we need to convert to a decimal form. The first number is 1.9 times 10 to the fourth meters. I keep forgetting the units, but we're not, the units are just kind of gratuitous. They aren't really necessary in this case when we're just converting the number from one kind of notation to another. Okay, 8 is 4.8 times 10 to the second seconds. 9 is 1.45 times 10 to the minus 2 meters. And 10, we have 3.4 times 10 to the minus 1. Okay, so those are our numbers that we want to start with. We're converting from a scientific notation to decimal form. You can pause the video and try it yourself, and then we'll come back and compare what our results were. Okay, so you can pause now. And hopefully you've gotten some answers for those. And when we come back, we can now try doing these. So let's see, 1.9 times 10 to the fourth. A positive exponent means you need to move the decimal point in the direction that makes the number bigger, and you move it 4 spaces. So 1, 2, 3, 4. So we have 1, 9, followed by 3 empty spaces. And when you basically have empty spaces before the decimal point, you fill them in with zeros. Don't actually write the decimal point in, though, because that would change the number of significant figures. This number here, the original scientific notation, only had 2 significant figures. And this number here, 19,000 with no decimal point, that has 2 significant figures because the zeros at the end don't count. If you put a decimal point in, now it's got 5 significant figures because those zeros at the end count. So leave it out. And the unit would be meters. Okay, so that's the first one. 6.39 times 10 to the minus 3. For that, since it's a negative 3, you have to move the decimal point in the direction that makes the number smaller, 3 spaces. So there's 1, 2, 3. So you have point, and again, you fill in the empty spaces with zeros, 0, 0, 6, 3, 9 cubic centimeters. So we've got 0.00639 as our answer. Again, those zeros at the beginning do not count because zeros at the beginning never count. This number here had, the original number had 3 significant figures, and our answer has 3 significant figures. Okay, 4.8 times 10 to the second. It's a positive exponent, so you have to move the decimal point 2 spaces in the direction that makes the number bigger. And you end up with 4, 8, and an empty space, so you fill that in with a 0. But again, oh, and it's seconds for the unit. Like part A, there's no decimal here. Because again, if you put a decimal point there, then the 0 would count and you'd have 3 significant figures, whereas you only want 2, because that's what the original number had. So 2 significant figures. All right, the next one is 1.45 times 10 to the minus 2. When you have the decimal point here and you have a negative exponent, you move the decimal point in the direction that makes the number smaller. We move it 2 spaces in that direction. So it ends up here. And so we end up with point. There's an empty space, so you fill that in with a 0. And then 145. And don't forget the unit. Again, this number has 3 significant figures because the 0 at the beginning doesn't count. The original number had 3 significant figures. And so that remains the same. That's a good sign. We have 3.4 times 10 to the minus 1. Again, negative exponent means make the number smaller when you move the decimal point. We only have to move it one space, and so we end up with 0.34. We want to leave it as 0.34 because that's two significant figures, and the original number was two significant figures. And as you may have noticed, when we're being formal about things, when there's a decimal point at the beginning of a number, you put a 0 in front of the decimal point. That's just a convention to kind of make sure that it's clear where the decimal point is. But when you're writing things by hand, that's not really strictly necessary, as long as you make sure that you make it clear that the decimal point is at the beginning of the number like I did here. So if you want to write this as 0.34, that's okay, but if you want to write it as 0.34, that's acceptable too, as long as you make the decimal point clear. And the same with this one. You could write that as 0.0145, or you can just write it as 0.0145. Saves a little bit of effort not to put that original 0 in. Okay, and Roman numeral 3 is actually about engineering notation, which I said we weren't going to do, but it's also useful from the point of view of recognizing what the metric prefixes mean. Okay, so what we're doing here is replacing the exponent part of the number and the exponential part of the number, remember, is just the part where you take 10 and raise it to a power. With a metric prefix instead. Because that's essentially what metric prefixes are. They're multipliers, you know, as I mentioned, they're multipliers which correspond to a certain factor of 10. So you could have, and I'll work out an example and then I'll let you try the rest and then we'll compare results. If you had something like 3 times 10 to the third meters. Well, 10 to the third is what the prefix kilo means. So replace that with kilo, and we have 3 kilometers. You can use the abbreviation K for kilo, and the abbreviations for the other prefixes too. So 3 times 10 to the third meters would be equivalent to 3 km. Which is 3 kilometers. So that's the kind of thing we're doing for the rest of these examples here. So number 11 is 4.6 times 10 to the minus 3 meters. 12 is 8.4 times 10 to the third meters. 13 is 12 times 10 to the minus 2 meters. That's actually, note that that is actually not proper scientific notation because the first part of the number is not between 1 and 10. But that's okay. I mean, unless I'm asking for a proper scientific notation, it doesn't really. Well, actually, I mean, if you're answering a question like on a test or a quiz, your answer should be either in proper scientific notation or proper decimal form. Number 13 here is neither one. That's not a proper decimal form because it involves an exponent, but it's not proper scientific notation because the first part of the number is not between 1 and 10. But as set up to a problem, we can kind of make an exception because what we're really looking for is what prefix corresponds to 10 to the minus 2. So we'll kind of let it slide. The next number is also not proper scientific notation. It's 84 times 10 to the minus 1 meters. And then there's 15, which is not scientific notation either. And that's 16 times 10 to the 6th watts. The thing about the metric system is there are all kinds of units that are metric units for various quantities. And capital W is one that we haven't seen before, because it stands for watts. That's a unit of electrical power, you know, like a 40-watt light bulb. The wattage is the rating of the light bulb's power. Or you measure the amount of energy you use in your home in kilowatt hours. That would be number of thousands of watts times the number of hours that you use them. And watt is considered a metric prefix, so you can use, or sorry, a metric unit, so you can use metric prefixes with it. So, you know, like I said, kilowatts, megawatts, whatever, milliwatts. If you look at the back of your cell phone, you'll probably see the power rating in something, you know, several, so many milliwatts, because they don't use a lot of power. But anyway, let you just pause the video there, try these, and then we'll see what we get. Okay, so you can pause now. And if you're back, we will compare notes. The part of the number we're concerned with here would be the exponent. So we know that it's going to be 4.6 something. 10 to the minus 3 means corresponds to 1/1000th, or 0.001. And that is the prefix, whoops, it's off the edge, milli. Okay, so this would be 4.6 millimeters. Or for short, 4.6 mm. Okay, the next one is 8.4 times 10 to the third meters. Well, actually, we saw that up here. 10 to the third corresponds to kilo, and so you can just use km, or you can write it out as kilometers. So 8.4 kilometers, or 8.4 km. 12 times 10 to the minus 2 10 to the minus 2 is 0.01, or 1/100th. And in metric prefixes, that would correspond to centi. So this would be 12 centimeters. Or 12 cm. And then in the next one, we have 84 times 10 to the minus 1. 10 to the minus 1 is deci. That is a prefix that's not used all that often, oddly enough, but we usually just, if we have something like deciliters, rather than saying so many deciliters, in most cases, we just say like so many tenths of a liter, because 1/10 is what deci means. So 10 to the minus 1 equals 0.1, or in other words, 1/10, and that is deci. Okay, so this would be 84 decimeters. Or 84 dm. There are some medical applications in which I think blood alcohol content, for one thing, is measured as like so many milligrams per deciliter of blood. So it's used in that context sometimes, but otherwise not used very much. Okay, exponent here is 10 to the 6th. 10 to the 6th is 1 million of something. And that would be the prefix mega. So 16 times 10 to the 6 watts would be 16 megawatts. And as the example showed, the symbol for watts is a capital W. You don't really have to know that right now. but the symbol for mega is capital M. So if you wanted to write it in shorthand, it would be 16 capital M capital W. Okay, so hopefully you're doing pretty well on these. If not, then you can always go back and watch the video again for more practice. And there will be practice in the homeworks too once I assign them. And in this case, let's see, Roman numeral 4 on the next page or the back of the page, depending on how you're looking at this. We have an example. Okay, so what we want to do is replace the metric prefix in these replace the metric prefix in these numbers with a power of 10. And if that does not result in proper scientific notation, then change it to proper scientific notation after that. So, for example, if we had, let me see if I choose one that's not there. Yeah, okay. So let's say we had 18 millimeters, and we wanted to replace milli with an exponent. 18 millimeters would be equivalent to 18 times 10 to the minus 3 meters, because 10 to the minus 3 is what milli means. Okay. So 18 millimeters could also be considered 18 times 10 to the minus 3. That, though, is not proper scientific notation. So we have to find the decimal point, which is implied after the 8 there at the end of the number. And we have to move that decimal point so that this first part of the number is between 1 and 10. To do that, you have to move it one place to the left, and that then becomes 1.8. Okay, 1.8. In moving the decimal point, we made the number smaller. 1.8 is definitely smaller than 18. So we have to make the exponent bigger to compensate by 1. Remember, though, tricky with negative numbers, if you're going to increase negative 3 by 1, it becomes negative 2. So in proper scientific notation, it would be 1.8 times 10 to the minus 2. So that's the kind of thing we're looking to do in these examples. All right, so number 16, as before, I'll set it up and then you can pause the video and try it on your own. 65.0 centimeters. Then we have 95 kilometers. Then we have 1.5 decimeters. And then we have 2.8 gigahertz. I'll explain in a moment what hertz means. But for right now, it's really only the prefix that you have to be concerned about. And giga was on the list that I gave you yesterday. So you can use that to convert. And then we have 35 milliseconds. Okay, so actually you don't even have to pause the video because I see here we're at half an hour. So I'm going to actually stop this segment of the video now, and I will continue on with the answers to this in the next part of the video, part B. Okay, so see you in a minute.